Hello everyone. For this tutorial video, I'd like to explain how to figure out the derivative of exponential and logarithmic functions, starting with the literal definition of the derivative per usual. If we take function of x plus h minus function of x all over h as h approaches 0, and replace the functions with the appropriate a of x, so we have a to the power of x plus h, minus a to the power of x all over h, as h approaches 0, we can use a property of exponents to break a to the power of x plus h as a to the power of x times a to the power of h. We next see a to the power of x is a common factor, so it factors out, and we have a to the power of h minus 1 times a to the power of x. Because a to the power of x does not involve h's, we can treat it as a constant and factor it out. We see the derivative of the function, if we choose x equals 0, is the derivative at point 0 times a to the power of x. Unfortunately, even though we correctly used the literal definition of the derivative, we get the function we wanted to find the derivative of in the first place inside the derivative. So we will not be able to find the actual derivative until later when we study how the chain rule works. However, we can find the derivative of one specific type of exponential function, which is e to the power of x. As we can see from a graph of it, the limit of e to the power of h minus 1 all over h equals 1. So the derivative of that function is e to the power of x times 1 is e to the power of x. Therefore, the derivative of e to the power of x is simply e to the power of x. Before we can differentiate logarithmic functions, we have to first prove the derivative of inverse functions, and be familiar with what inverse function actually refers to. Algebraically, two functions are inverses of each other if, and only if, function 1 of function 2 of x gives us x, and function 2 of function 1 of x also gives us x. A graphical definition of this is, two functions are inverses of each other if you can flip the graph of one across the origin, or along both x and y directions at the same time, and get exactly the graph of the other one. An algebraic proof of the derivative of inverse functions involves the chain rule as well, because of the fact inverse functions involve compositions. So we will stick to a graphical proof instead, and see that if we draw two lines that are tangent to these two graphs, we see, because we remember the derivative is the instantaneous rate of change, that the derivative is the slope of these tangent lines, and we see graphically that these slopes can be represented with 1 over the other slope. In conclusion, the derivative of function 1 equals 1 over the derivative of function 2. So now that we have proven a formula for the derivative of inverse functions, we see that e to the power of x and ln of x are inverses of each other from the graphs. So we plug in the appropriate formula. We remember the derivative of e to the power of something is simply e to the power of something. So we have 1 over e to the power of ln of x, which simplifies to 1 over x, because of the algebraic definition of inverse functions. In conclusion, the derivative of ln of x is 1 over x. However, this is not the whole story, because x must be greater than 0 for the normal ln function to work. So if we instead take the derivative of ln of absolute value of x, we would allow ourselves to get negative values, because of how the absolute value function works. But we would see, at x equals 0, the function would still not exist. To prove the derivative of more general logarithms, we have to figure out a formula to relate general logarithms to ln specifically, which is called the change of base formula. We first notice, by definition of logarithm, if b to the power of y equals a, then logarithm with base b of a equals y. If we take a different logarithm, say logarithm with base d of both sides, we can rearrange the left-hand side to y times logarithm with base d of b equals logarithm with base d of a. What we saw earlier, by the definition of the logarithm, y is exactly equal to logarithm with base b of a. So now we get the logarithm with a different base by itself, compared to the other two. by dividing the right-hand side by the logarithm with identical base on the left-hand side. In conclusion, logarithm with base b of a equals logarithm with base d of a over logarithm with base d of b. Since we have proven a formula for the change of base, we take the derivative of this change. We see because we are taking the derivative with respect to x, ln of a is a constant. Therefore, we factor out 1 over ln of a and get the derivative of ln of x, which we know the derivative of already. In conclusion, derivative of logarithm with base a of x equals 1 over x times ln of base a. Since we have figured out the derivatives of inverse functions in this video, we can figure out the derivatives of inverse trig functions in the next tutorial video using this definition. Don't forget to subscribe if you found this video informative, and make sure to see the other tutorial videos, and follow me on either Facebook or Twitter for more content.